Assalamualaikum and salam sejahtera. We are from Group B. Would like to present about CFD for fluid mechanics, laminar parallel flow over a flat plate. So this is my team member. We are from Group B. I would like to introduce ourselves. My name is Adriana Shikin binti Muhammad Zain. My job scope is conducting theoretical research and advising the objective for theories behind CFD simulation. Next, my member is Pavindran, anak lelaki Chandra. His job scope is simulation in the field of CFD for airflow 1.5 meter per second. Next is Manoj Kumar, anak lelaki Kila Silver. His job scope is simulation in the field of CFD for airflow 1.0 meter per second. And the last is Nordiana binti Samsul Bahri. Her job scope is compare and analysis to highlight the process of evaluating the CFD domain. So this is our table of content. We have introduction, theory, objective, geometry, detail and dimension, method, result and comparison between result and theory. So this is our introduction. The introduction of the presentation on CFD for fluid mechanics laminar parallel flow over a flat plate sets the stage for the study. It explains the significance of laminar parallel flow in the context of aerodynamic and heat exchangers. This section highlights the importance of understanding the boundary layer, a key concept in fluid dynamics. It serves as an overview, providing a context for why studying the laminar flow over a flat plate is essential in both theoretical and practical application in the field of fluid mechanics. Next is theory. The theory of laminar parallel flow over a flat plate is an important concept in fluid dynamics and aerodynamics. This scenario is often used as a simplified model to study the behavior of fluid flow over a solid surface, and it serves as the basic for understanding more complex flows. So this is a diagram of laminar flow. So the first theory is flow profile. The velocity profile within the boundary layer is parabolic, with the maximum velocity occurring at the center of the boundary layer and decreasing to zero at the surface. This profile is often described by the Brand boundary layer equation. The second is laminar flow. Laminar flow refers to a smooth and orderly flow of fluid, characterized by layers of fluid sliding over one another with minimal missing between the layers. In the context of a flat plate, the flow is assumed to be laminar for certain conditions. And the third is Reynolds number. The Reynolds number is also a crucial parameter in this context. It helps in predicting the flow regime, laminar or turbulence, based on the fluid properties, flow velocity and characterized length. The presentation delves into the Blasius solution, which provide a mathematical description of the velocity profile in the boundary layer for laminar flow condition. So the Reynolds number is, this is a formula, velocity multiple length over nu, which is the velocity profile in the boundary layer for the parabolic distribution. The Blasius solution for laminar flow over a flat plate provide expression for velocity profile. As we know, for this simulation we will use for linear profile character, which is u over u equal to y over sigma. So as you can see, there are other profile character which is for parabolic, cubic and sine wave. Next is boundary layer formation. A Blasius boundary layer is named after Paul Richard Heinrich Blasius. As fluid flow over a flat plate, a boundary layer develops near surface. The boundary layer is region where the velocity of the fluid changes from zero at the surface to the free stream velocity away from the surface. In laminar flow, this boundary layer is smooth and well ordered. Next is Blasius solution under the boundary layer formation for laminar flow. For a flat plate with laminar flow, a classical solution to the governing equation was provided by Heinrich Blasius. This solution describes the velocity profile and the boundary layer thickness along the flat plate, which is sigma equal to 4.91x over square root Reynolds number, or we can use 5 multiplied x over square root Reynolds number. X is the length of the plate. I will continue. My presentation is our objective in this study are to investigate the governing equation for laminar parallel flow over a flat plate. to determine the influence of various parameters such as Reynolds number, flow properties, plate properties, and geometry of the flow behavior. To analyze the flow features, including flow velocity and velocity profile. Number 4 is to assess the flow stability and separation characteristic. To provide guidelines for optimal design and control of fluid flow around a flat plate. To simplify the study, the flat plate can be considered as an infinity plate with negligible surface roundness. The flow is assumed to be parallel to the plate and can be modeled using potential flow theory.
In this part of the video, I'll be explaining the geometry details and the dimensions that are crucial for our CFD simulation of a flat plate. As you can see in the schematic diagram, we are dealing with a classic laminar flow situation. The plate has a vertical dimension denoted as V of 1 meter and a horizontal dimension H of 1.0 meter. These dimensions are essential for setting up a simulation domain. For our simulation, we are considering two scenarios for the airflow velocity, which is U. The first scenario is at a speed of 1 meter per second and the second at 1.5 meter per second. These velocities represent different flow conditions that our flat plate may encounter. The arrow shows the velocity profile of the air as it moves over the plate, with U infinity representing the free stream velocity above the boundary layer and U showing the velocity at various points within the boundary layer. Our focus for data analysis will be along the middle line of the plate, as this is where we expect to see critical characteristics of the flow that are representative of the overall behavior.
We start by creating the geometry for our project. Firstly, we start with creating the horizontal and vertical lines. Check the horizontal value is 5 meters, while the vertical value is 1 meter. Then we generate our geometry. After that, we continue by creating the mesh. Generate the mesh. This is roughly the mesh that we get. If it's not enough, we insert face meshing and generate the mesh now. This is the mesh that we get. Then we insert sizing, and we click on each edge. We control and click on both the edges, click apply, and then select number of division, which we import with the value of 50, and then behavior hard, and we generate the mesh. So the mesh that we get, we insert another sizing. Next, we click on the left edge and insert the number of divisions, which in this case is 60. Change the behavior to hard, and we add a bias for this. The bias factor will be 70. Next, we generate the mesh. This is roughly the mesh that we get. Next, we add another sizing. For the right side, we add the number of division as 60. And we change the behavior to hard again. We add a bias. The bias factor will be 70. Each time we add a reverse bias. Click on the edge and click apply. So that generate the mesh. This is roughly the mesh that we get. Next up, we assign names for each of the sides. Firstly, for the face, we assign the name airflow. Next, click on the edge, add name inlet. Click on the right edge and create name selection. Add the name as outlet. Next is plate, followed by far field pressure. Next up, we set up and we add up a precision, add 4 solver processes. We check our solution, check our mesh. This is what we get. These are the results down there. click fluid and air, change the settings as stated there. Next up, we go to boundary condition. On plate, these are the settings. Just leave it as it is. Next, go to inlet. This is where we change our velocity magnitude. For our group is 1. Click on apply. Leave everything as it is. Now we go to pressure outlet, leave everything as it is. Next, far field pressure, we change the type to symmetry. Next up, go to method, change schemes to simple scheme. Leave everything as it is. Go to monitors and residual. You only need the continuity, X velocity and Y velocity. Change the criteria to 1 power of negative exponent negative 6. Go to initialization. Click on standard initialization. Leave the rest of the setting as it is. Change the compute from to inlet. Click on initialize. Values will change. Next, go to run calculation. We change the number of iterations. On calculate, and this is the graph that we get. This is the number of iterations that we get. Now we can change the value here. We change the value to 1 exponent negative 7. Calculate. These are the new values that we get. Next, you can check on the results. Select to contours, select velocity contours, and click on display. Next, we go to results. Select contours, add contour, contour 1, select symmetry 2 as a location, click on apply. Now this is the pressure contour that we get. Change the number of colors to 50, you can see more variations. That is the velocity contour, you can change it by changing the variable to velocity. This is the velocity contour for the graph. Our point is the middle point, so we add the middle point of our plate. These are the middle points of our plate: 0.25, 0.25, and 0.5. So show the middle point. Click on apply. The location, we change to line 1. Click on apply, and this is the graph that we get. Click on change the samples to 100. This is the more real graph. Now this is the graph that we get. Now for the 1.5 velocity magnitude, we just need to change it to from 1 to 1.5. The rest is the same. We follow these exact same steps in this video. The only thing we need to change is the velocity magnitude, which in this case from 1 to 1.5.
So in this part of the video, I'm going to explain the velocity profile contour of two different flow rates. So there are some color gradients are used to show their phase inside a certain area. On the left, we can see how the fluid behaves when it's moving at the speed of 1.0 meter per second, with red areas where it's moving quickly and blue where it's moving slower. On the right, the speed of the flow rate is up to 1.5 meter per second and the colors shift indicating everything moving faster. By examining these colors coded maps, we can predict how changes in speed affect fluid flow. This kind of information is super helpful whether it's for installing heating and cooling systems, for example, designing equipment in hospitals, or even making cars and planes more aerodynamic. It's all about making sure things operate smoothly, efficiently, and now I'm going to explain the pressure profile counter obtained from the CFD simulation. The visual displays the result of fluid flowing at two distinct velocities, which is 1.0 meter per second and 1.5 meter per second, within a constrained geometry. The contour plots vividly map out the pressure distribution, with varying hues denoting different intensities. Darker shades correspond to lower pressure, while lighter shades indicate higher pressure. At the lower velocity, we observe a more uniform and gradual pressure gradient, which is indicative of a laminar and stable flow. Conversely, the simulation at the increased velocity reveals a steeper and more varied pressure gradient, hinting at the onset of a turbulent flow or increased initial forces at play. These simulations are crucial for predicting and optimizing flow behavior in various engineering applications. Based on the graph from the CFD simulation, we can observe the convergence of velocity with respect to the number of iterations. This graph is pivotal in demonstrating the stability and accuracy of our simulation. The graph plots three distinct variables, which is continuity, x velocity, and y velocity, against the number of iterations performed. As the iteration progresses, we notice that the residual values of all three variables decrease, which is indicative of the solution approaching convergence. Notably, the residuals drop significantly as we increase the velocity input from 1.0 meter per second to 1.5 meter per second, suggesting that our model responds well to changes in velocity inputs. The consistent downward trend across the iteration underscores the reliability of our simulation setup. This insight is crucial for validating our CFD model and provides a solid foundation for further analysis and optimization of the fluid flow parameters in our system. Now I'm going to explain the result that we obtained from the CFD simulation for the 1.0 meter per second flow rate. In this graph, we are presented with the result of the CFD simulation that illustrates the velocity profile, which is denoted as U, across a vertical cross-section, which is denoted as Y. The profile shows velocity values at a steady 1.0 meter per second across most of the domain, with a sharp increase as we approach the boundary. This sudden spike could represent a boundary layer effect where the fluid velocity adjusts from a non-slip condition at the wall to the free stream velocity further away. The almost flat velocity distribution across the majority of the graph suggests a well-developed flow, which is typical in internal flow scenarios like pipe flow after sufficient run length. This type of velocity profile is crucial for understanding fluid behavior in engineered systems, as can be instrumental in optimizing flow conditions for various applications such as reducing drag in pipes or designing more efficient fluid transport. So this is the result for the 1.5 meter per second flow rate. This graph showcases the result from a CFD simulation depicting the velocity profile designated as U against the vertical axis Y at an increased flow rate speed of 1.5 meter per second. The velocity distribution remains consistent at and near zero across most of the cross-section, indicating a laminar flow with minimal velocity gradient in the central region. Toward the boundary, there is a steep gradient leading to a pronounced peak, which is characteristic of a boundary layer developing in response to the wall's no-slip condition. This sharp change in velocity near the wall is a classic indicator of the fluid's adherence to the boundary and the resultant shear effect. The graph shape suggests that the flow is well developed and that the simulation parameters are set correctly to capture the boundary layer phenomena at this higher velocity. These results are integral for understanding the effect of increased flow rate on the fluid dynamic within a system and can inform decision on flow
Next
management.
is I would like to explain about comparison between result and theory. First, about boundary layer thickness. By using Blaise's equation but using theory method, we will get the value of boundary layer. We will use the Reynolds number for laminar flow, which is 5 times 10 power of 5, and the equation for boundary layer thickness is sigma over x equal to 4.91 over power root Reynolds number. So our length given is 0.5 meter, and put it in the equation and we will get 3.47. Next is u over u equal to y over sigma, which is we will get 0.3, 1 over 3.47. So we compare the result and the theory. For the airflow 1.0 meter per second, the boundary layer thickness in the graph is the same with the calculated using Blaise's equation. And for the flow 1.5 meter per second, the boundary. Next comparison is velocity profile. As we know, the velocity profile in the boundary layer follow a parabolic distribution. Linear profile character is used to find the velocity profile for our dimension using theory method. The equation is u over u equal to y over sigma, which is 1.0 over 3.48. We will get 0.3. From the result for the airflow 1.0, the intersection found of the velocity profile at 0.3, which is the velocity profile from theory method, and the final result is the same. And for the airflow 1.5 meter per second, the intersection found at 0.2, which is different from the theory method. So this is the way we will find the velocity profile for the final result. At the left side is for airflow 1.0 meter per second. We will make a line at 1 at x-axis and find the intersection between the line of graph, and we will get 0.3 at y-axis. And that is the velocity profile for 1.0 meter per second. At the right side is for 1.5 meter per second. We will make a line at 1.5 at x-axis and find the intersection at 0.2 at y-axis. So that is the velocity profile for 1.5 meter per second. So that's all for our group. Thank you.